All right, folks. The topic of today's paper is quite interesting. It says one initialization to rule them all. Fine-tuning via explained variance adaptation. It is a relatively short paper, actually, or rather a set of two papers. Like one is the paper, and then there's the appendix, which goes into considerable detail. The paper itself, the main paper itself, is relatively short. It's just 10 pages. Nevertheless, it needs certain amount of background to fully appreciate what it has. Now, there is another paper effect, or rather not paper, another supplementary material at the end of it, which is almost written like a separate unit or chapter, which follows and gives you all the technical details of how they went about doing it. Like, for example, they'll tell you that they used 4 A100 GPUs to do the fine tuning and so on and so forth. Now, this paper requires certain degree of background. And so before I read this paper, I would like to briefly go over the background. It needs two sorts of background, a little bit about machine model fine tuning and how, and one of the approaches to fine tuning called performance, sort of parameter efficient fine tuning. In particular, the PEFT method called LoRA, which is perhaps the most dominant PEFT method. So I'll briefly introduce it for those of you who don't know what that means. And that would be one background that we need to understand the work. The second background is a little bit mathematical. It has to do with one of the crown jewels of linear algebra, singular value decomposition. Now, the moment we talk about singular value decomposition, people tell me that, well, it's been 10 years, 20 years, 30 years since I studied that in engineering colleges. And even then, it wasn't one of their favorite topics. So I would like to bring it back, but I'll do it in a sort of in a slight cheat way. I will do it by explaining a close cousin of singular value decomposition called eigenvalue decomposition, because the intuition of singular value decomposition is more or less aligned with the intuition of eigenvalue decomposition. Once we understand that, understanding this paper and the work that has happened around this paper should become straightforward. So let me first go over these two prior background that we need to explain this paper, and then we will come back to this paper, which, given the background, should be pretty easy. I have to, let me situate myself a little bit. So when you create a large language model, let us say that you have a model like a big model with its billions of parameters or hundreds of billions of parameters, billions of parameters. Now, when we think of these, we usually think of LLMs or transformers, but it need not just be large language models or sort of the decoder models. It can be any transformer. So let's generalize our thinking and think it could be any transformer. Or more generally, it could be any neural network. So whenever the broad class of neural networks, and there are many neural architectures, this particular consideration applies to all of them. We live in a world in which if you take a really large neural network and try to train it, then the neural scaling laws kick in. What does that mean? Well, these three things go together: the size of the data, data size, model size, which is what you call the billions of parameters, and how much compute you throw at it, compute size. So how many iterations, epochs, steps of training you went through. Now, the way it works is that they need to go more or less coherently together. If you take a small model, then reasonable data set sizes can train it, and the compute needed will not be that much. But as you scale the model up, more and more data is needed to train it, and therefore more and more compute is needed to work with it. So otherwise, and so these are called the neural scaling laws. The question is, why would you want to create bigger and bigger model? Well, the thing that happens is bigger models tend to have more abilities. They tend to have stronger, what appears to be reasoning capabilities, though reasoning is rather a strong word and highly contested. But let's just say that it is a simulacra of reasoning that they can exhibit. And these models tend to do that. They begin to do reasonably good at basic arithmetic and so on and so forth. So people tend to create large models. And similarly, in the field of computer vision, when you create, it is a known fact, and we have known it for a decade, that if you, for example, create a convolutional network, let's take a very basic thing, just one or two convlayors, its performance for any downstream task, classification, or creating an autoencoder out of it, convolution, and then transpose convolutions or deconvolutions, and then doing reconstruction. Any one of those tasks, you will not see as good performance as when you create really deep convolutional layers, right? And so when you do that, though, the big problem that comes is this: the compute size and getting even access to data sizes. It just so turns out that the bigger the model you train, the fewer the people there are in the world who have the compute infrastructure or ability to run computes of that size. We begin to talk of the hyperscalers. We begin to talk of the Googles, the Meta, the Microsoft, the OpenAI of these, and the X and whatnot of the world. And these are very select few people who can alone train this model. And also we know, unfortunately, that bigger models are better, broadly speaking. And so there's a tradition that arose, which was transfer learning. And obviously, I'm speaking the very basic facts, and I apologize if this appears too elementary to most of you. Transfer learning was the concept that people with the right resources who can train big models, they will train the big model, and then they will give it to you. They will train the big model, and the so-called foundational big models are foundational models, which is literally mentioned in the very first line of this paper, foundational models. As it says, foundational models are usually trained on large-scale data. And then what happens is, once you create a foundational model, FM, you release it, or the tradition was in the industry that you would release those models to open source. Then normal people, or small startups like you and me, or everybody else who is not a hyperscaler, would go perhaps to Hugging Face, to somewhere, PyTorch Hub, and we would download those models. Then we would hope that these foundational models are good enough for our task. For example, and just to recap a bit of history, originally BERT was trained on a masked language as a masked language model. What it means is, you take the cow jumped over the moon, you hide the word cow, and then you ask it, make it guess what jumped over the moon, right? So, and you train it to say cow. That sort of training or supervised learning by masking, creating supervised learning by masking, though it is not really supervised learning because you don't have labeled data, but you artificially create labeled data by masking a few words here and there, and then loading it, then converting it somehow, a vast amounts of data, web data, into essentially XI and YI, in other words, input-output, and then training the machine with it. It turns out, trains that foundational model BERT. Now, it turns out that when it gets trained, it is good at a lot of downstream tasks, not just filling in the blanks. And it's able to do classification, it's able to do all sorts of things, sentiment analysis, and so on and so forth. Now you can ask this question, why was it able to do? Why are these foundational models able to do it? The point is, you train the foundational model on a task that is generic enough and may even be somewhat meaningless. Like, for example, masking a few words and asking it to guess. But the reason it works is because there is no way a machine could have done that task successfully without foundationally understanding language itself, deeply understanding like the structure of human language itself and its semantic. Right? And therefore, the machine has developed language understanding. That foundational model has developed language understanding. So that is the concept of a foundational model. It is imbued with fundamental properties, which out of which or which facilitate downstream tasks. Right? So what would happen is, suppose you want to do some task, some classification task. You can use a foundational model and try to do that. But it may work well enough. If it works well enough, and these foundational models, the word that people use is pre-trained. These are pre-trained and released, pre-trained models. Then if you need it, and if your needs are not fulfilled, so for example, you take a foundational model and you give it your data, your own data, which I'll call D prime, and then you notice that the performance is suboptimal. Right? There is scope for improvement. So then what you do is that you say, all right, let's go through further training of this model. We will unfreeze the weights and biases of this neural network, and we will pass it through our data, fine-tuning. This process is called fine-tuning. It is also training the model, but training the model not by taking random weights or completely from scratch, but keeping the weights and biases that the foundational model inherited from pre-training. So then what happens? It is like, it's like saying that you know how to speak English. You just need to develop a British accent. A small gap. The learning of the English takes years. Picking up an accent, perhaps, especially if you're young, I suppose, is a much quicker task. Or writing in a British style, making sure all the words are they have less of Z and more of S, right? Would and not be as hard a task relatively. So sometimes you need to do things that the foundational models are not capable of, but it's just adjacent to it. You just need a little refinement or fine-tuning of the knobs within the model. And therefore the term fine-tuning. Fine-tuning is usually a supervised learning task. And you do that because you may give data. For example, you may say a sentence and you may say, for example, if it is sentiment analysis, you can tell whether it is positive or negative, right? You can specify what it is and you can give it a lot of data. This will say plus, this will say minus, this will say plus, this will say plus, and so on and so forth. And then you train this data, you again would feed it. For example, this becomes a classification problem. You can further train it with a cross entropy loss, for example, a negative loss, log likelihood loss. And then what you have is finally a model that now serves well, or that is the theory. However, in practice, there are quite a few problems in trying to fine-tune, in the traditional sense, a foundational model. So what happens with foundational model is that, first of all, to fine-tune a foundational model, you need to load the entire foundational model in memory. Let's take a 7 billion parameter model. So I am speaking now to the problems with limitations of foundational models. Hang on. Limitations of, and this approach that we are saying, it is often called the full fine-tuning because we'll encounter an approach that is contrary to it, that doesn't do that. When limitations of full fine-tuning are A, need more hardware, heavy hardware. So let's take it. Today, circa 2024, most of us are sitting on our workstations with a 4090, right? RTX 4090. That RTX has what, 24 GB VRAM. So, which is why very common for us to play with 7B or less than 7B billion param model. Why do we do that? Because a 7 billion parameter model, we can load in memory, and if we use 16-bit floating point operations, this amounts to 2 bytes per parameter. Now, in the forward direction, when you send it a X input, the forward pass, the fx, when you say that I'm just going to do the forward pass, f of x to produce y hat is equal to fx, this neural network, all it needs to do is a whole series of matrix multiplications and activations. Alternatives, matrix multiplications, activations, matrix multiplications, activations, and so on and so forth, right? Linear and nonlinear transforms, layers after layers. And whether it's convolutions, whether it is feed-forward network, ultimately, it's a game we play, right? Now, the input, so one basic rule is that the total memory utilization would be just in the order of, let's say, so 14 billion. So we need 14 GB. Why? Because 7 cross 2 is 14 GB. Add a 20% plus 20% overhead is approximately 16 GB. So we are able to run inferences with the 16 GB of memory, which means we feel pretty pleased with ourselves because we have a 24 GB 4090, let's say, and we say, yay, it works just fine. And which is why, obviously, the 7 billion parameter models are so very popular. On the other hand, if you were to do full fine-tuning of this model, right, what would you have to do? You would have to unfreeze all the parameters. And now you'll have to so now what happens is, if you do training, full fine-tuning, let's work it out. Maybe I'll use another color here. Well, oh, that's pretty flat. I apologize. I have to. Full fine-tuning, what does it involve? Let's figure that out. Full fine-tuning would mean I need a 14 GB for the parameters, right? Or for the params. But you know that in X goes in, you compute y hat is equal to f of x, but then what do? You need to compute the loss with respect to y and y hat. You take the gradient of the loss. You have to take the gradient of the loss with respect to each of the parameters in your model. Let me write the parameter as theta. And obviously, I have erased all the subscripts to keep the thing easier to understand. So you would know. So we know if you have gradient, what you have to do, you have unfrozen the model. Now, fortunately, things like PyTorch are auto-differentiating framework. The moment you unfreeze the thing and you enable auto-differentiation, now you need another 14 GB for parameters, for the gradients. Isn't it? And you already realize that you have exceeded the capacity of your RTX 4090 right there itself, right? So it is hard to fine tune. So now you say, okay, I need A100 or I need something bigger, right? But it gets even worse actually, because you don't need just the gradients. If you use any of the modern optimizers for the learning step, right? And just to whet your recollection, your learning step is a theta next is equal to theta minus some learning rate scheduler and some function of the gradient of theta. So these days, you use a complicated function of the gradient, right? And usually this function contains the gradient term as well as it contains If you're using the Adam optimizer, it contains a quadratic term, right? And so by the time you look at that, you realize that you need another 14 GB for quadratics. And now you look up the sum of it, and you don't feel very pleased with yourself because this is 42 GB right there, right? And at 42 GB plus 20% overhead, that 20% almost looks like the state tax here in California these days, right? So then it doesn't look very, very nice at all, because 50 GB, and at 50 GB, you realize that even if you just bought A6000 with 48 GB VRAM, you're still in trouble. So then what are your options? You can go about quantizing. So people play this quantization game. They say, hey, 2 bytes per parameter is perhaps not necessary. We'll go with 1 byte per parameter, 8-bit quantization. Sort of works. Then people feel, oh, it doesn't fit into my 4090. If you do 8 bits, now you can take half of it and it will become by 2. So it becomes 25 GB. You realize, well, that still doesn't fit into your 4090. You say, what do I do now? Maybe I'll go down to 4 bits. So you go to 4 bits. And then, of course, there are people who go to 2 bits, like basically saying, is it positive, negative, or 0, right? And people play this game, and in the open source, it's been quite a bit, this quantization game that, for certain tasks, the model can be quantized down and it still works. It's a poor man's game. The reality is, the actual reality, of course, is the more you quantize, the more you lose performance. You slowly lose. By the time you come to 4-bit, you lose quite a bit. By the time you go down below 4-bit, opinions differ, but it is not a general purpose model anymore. It will work perhaps for some things and not for some things. One way to explain that somebody explained very well is like, if you just read a book or a paper, you remember all of it. That is unquantized model. 1 week later, what you remember is now an 8-bit quantized version, right? 1 month later, what you remember is a 4-bit quantized model. And 1 year after reading the paper, whatever you remember is your, right, lower than 4-bit quantization, right? So that sort of captures the intuition of how quantization works. So that's one problem with full fine-tuning. The other problem with fine-tuning that has been there is the problem of, even if you had the resources, people found that fine-tuning is a dangerous game. You're playing with fire because because of a problem called catastrophic forgetting. Catastrophic forgetting. What is catastrophic forgetting? What it means is that, see, the model was initially pre-trained on data. Let's call it the data D. This is your ginormous data. Right? The whole web scale data you train your model with. Now, let us say that the model has in data input space some distribution like this. It has some probability distribution, right? This data respects this. Huh? Like, okay, a PX, X sampled from D, it shows a probability distribution like this. But why do you want to fine tune? If you want to fine tune, is because you're solving a problem that is slightly different. It's adjacent. For example, an example would be a normal language model would consider a day where like if you say a bear versus bull, right? Normal language might infer something to do with animals. But in financial market, they have altogether different connotations, right? And so sometimes the reason is that the language understanding itself needs to change a little bit for the financial domain. What it inherently means is that your D prime's data even though it is a smaller data, its distribution is, let us say, different. I'll just make it deliberately exaggerate the difference. Let us say that it is like this. Now, when you train this machine with this data, this model with this data, what will happen is don't train it too long, because what it will do is it might come to the conclusion that this is wrong and this is right. Right? And it may say, oh my God, I really misunderstood the situation. Let me relearn it. And what it may do is it may sort of overfixate on your fine-tuning data. So one of the lessons people learn the hard way with full model fine-tuning is don't run it for too long. Right? Otherwise, you run the risk of catastrophic forgetting, even if you have the hardware resources. And which is why on the internet, you find a considerable debate about fine-tuning. Many people will say fine-tuning these big models is just a bad idea, or that it is unnecessary, or so many things keep coming up. The pendulum, it's sort of like the pendulums of war. There is one camp that says fine-tuning is absolutely necessary. There's another camp that says anything but fine-tuning. There's no need to fine-tune. Right? And in a metaphorical way, the two sides are at war. And whenever there is war, as you know, there's the pendulum of war. Sometimes one side seems to be winning with very strong arguments, and then something else happens, and something else happens, and some other research paper or finding comes through, and then the pendulum swings the other way. Right? And that has been happening back and forth. You can observe the debate that's been happening on the internet in this particular context. So now that we realize that full fine-tuning does come with problems, you need to have deep pockets. And even if you have deep pockets, you risk catastrophic forgetting. By the way, those are not the only problems. There's a host of other things, but we'll just stick to two major problems. Now let's come to an alternative to it. One of the first, there are many good alternatives that people found to full fine-tune. The goal of alternatives are, first, can we run it on reasonable, sensible hardware? In the case of you and me, a sensible hardware might look like 4090, or in a computer which has two or three 4090s. Right? For example, here at support vectors, our machines, we support typically 2 or 4 4090s. So can you fine-tune a machine on that? Or on some machine which has just one server with 8 A100s or 4 A100s or something like that. Reasonable hardware. Right? That is one goal. The second is, how in the world can we go and circumvent the risk of catastrophic forgetting? Right? So two problems. How do we solve that? So the approaches that came out, there are many approaches that came, but one large class of approaches that is very successful in this space, they go by the name of PEFT, parameter efficient fine-tune. And broadly what they do is that they tune. There are many ways to do that, but I will just focus on one of them, which was called LoRA. Broadly, what LoRA says, it stands for low rank adaptation. Low rank adaptation. Now, the moment you say low rank, it starts frightening people with nightmares of linear algebra, right? Because that's where we had all of this matrices and their ranks and whatnot. Right? So I'll try to make it very intuitive because I know somebody explicitly said to me before today in the morning that do whatever you do, except too much math. Right. Nevertheless, this paper is a little mathsy, unfortunately. So, but I'll try to make it as intuitive as I can. So we'll come to what low rank. Low rank is basically this. Suppose, and I'll give you the intuition of that is actually very easy. Suppose you are in three-dimensional space, right? But it so happens that there is actually a plane, right? A plane. And it turns out that all the points of your data or a surface, but let's take a plane, all the points that you have, they happen to reside only on that plane. Now, the plane may be tilted. It doesn't, as you can imagine, I've made a tilted plane, though I probably didn't do a very good job of it. The plane could be tilted at any angle whatsoever, right? But the points belong to that. Now, perpetually, when you look at the data, when somebody gives you the data, they give you a table of data with X, Y, Z, isn't it? This is the way, because each point has a X, Y, Z coordinate. So in other words, X belongs to, every point belongs to a three-dimensional space. Does that make sense? It belongs to a three-dimensional space. However, you could say that while that is true, if you observe very carefully, it actually belongs to only a plane. And a plane can be described using only two dimensions, isn't it? If I put a new coordinate axis on the plane and create a new X prime, Y prime, every point has a corresponding X prime, Y prime, isn't it? So the same point P can be represented as X belonging to three-dimensional thing, or it could be represented as X prime belonging to two-dimensional, right? So what it means, what does it mean? It means that if you took this entire matrix of data, and we won't go through all of the details, but and in fact, that's exactly the transformation we'll talk about in a little bit. But basically, there is a magical way to discover, there should be some way to discover that the data actually belongs to just a plane, a two dimensions, right? So we say, is 2 less than 3? Of course. 2 is lower than 3, right? And so we just discovered a low rank, right? A low rank. We found a smaller subspace that the data really belongs to, a lower. That is the intuition of low rank. Are we together? That's what it means. Now, it turns out that when you do that, the LoRa is a very simple concept. What it says, the basic LoRa says this. See, you have a model, a big model, foundational model. Keep it frozen. Like when I make this asterisk, it stands for snowflake, frozen, right? Take the input. Don't at all touch the foundational model. Let the output come out, y hat, let's say, or actually let the hidden states come out. In reality, it won't be, because you do it at every layer, the magic that we are going to do. So at every layer, you will have some hidden states coming out, logits coming out, but then do one thing. The same input, pass it to two matrices. A, that converts from, let's say X belongs to some dimensional space D. For the sake of argument, let's say D is equal to 100, right? Take a matrix that is A is 100 cross, let's say R. Let's say 3. I just took a number 3, very small number, 3. So this low number, R is equal to 3. You're saying that I am taking a matrix, which is 100 cross 3 matrix, right? And this matrix, 100 cross 3 matrix, is A. And you take the converse of it, B is 3 cross 100 matrix. So what will it do? A essentially projects data to a lower dimension. It is almost like A projects data, as in the above thing, into a lower dimensional plane, isn't it? Just a three-dimensional plane. Or if it helps you, just think two-dimensional plane, because we can all think in 2 dimensions, much better. So imagine that you project this high-dimensional data onto a page, right? And what does B do? B takes the point on the page and from that somehow does a transformation and reconstructs a vector back in 100 dimension space. So what can happen? X will go in, right? And A of X will be a matrix, will be a vector of, so A of X, let me just call this latent state H. Let me call this latent space Z. Z is equal to A of X. Z will belong to are two-dimensional. It will be a two-dimensional vector, isn't it? And then two-dimensional vector, this thing that comes out, let me just call it, what should I call it? H prime. H prime, right? H came out of this and H prime comes out of this. Then H prime, which is equal to B of Z, and therefore it is B of A of X, right? H will belong to back to a 100-dimensional space, isn't it? You project it back. Now you ask this question, why am I doing that? The reason you're doing that is, now look at this machine. In this layer, suppose you're going from 100 dimensions. Suppose you have imagine a neural net that has 100 input thing, and you are converting it to another 100, let's say. So what is the size of this matrix? 100 times 100, isn't it? 100 times 100 is equal to 10 to the power 4, 10,000. It has 10,000 parameters. On the other hand, when you do this, instead pass it, what is the number of parameters in, well, did I 100? When I do this, how many parameters do I have now in A? So this W has this. A has just 100 times 2 is equal to 200. And B has, again, 2 cross 100 is equal to 200. So A, B put together have total of 400 params, right? Now, what is the intuition here? You are saying that take this and add these two results and give it to the next layer. Next layer won't know because you're adding vectors of the same size. H and H prime are all, right? The vectors of the size that you want. And so instead of like fine-tuning a matrix of 100, like 10,000, you have a parameter size that is very small, 400, which explains the word parameter efficient. This LoRA model is parameter efficient because it's very few parameters. Now, what it says is that these A and B matrices are trainable. A and B are trainable matrices. What it means is the backpropagation, the gradient of the loss, will affect A and B. So pass data in fine-tuning, but when the gradient propagates back, gradient doesn't go to the foundational model. Yeah. It's a stop gradient. You don't, it's frozen. You only pass the gradient through the LoRA adapters. And so what happens? Only these weights get learned. But then you might say, now wait a minute, this looks like cheating. Can you really get away with this? Right? Can you, if I'm fine-tuning a massive model, instead of playing around at each layer with, let's say, 10,000 weights and weights that I have to update, I'm just updating 400 weights. Why would I get away with it? And the answer to that is very interesting, actually. See, the idea is that when you fine-tune, you're making small changes. You don't want the machine essentially to forget everything that it has learned. You want it to hold on to, for example, its language understanding, but you're just sort of teaching it a dialect, right? Small perturbations. And the basic hypothesis with LoRA is that small perturbations can be captured as somewhat like these points in lower dimension space, that they can actually be considered as those perturbations are best represented in a smaller subspace, right? Or and therefore with low rank matrices. And that's all you have to train, right? The sum total of all the changes can be done. And so that is the concept of LoRA, which is explained by this. So when you look at this equation, this equation basically says that W dot X is the initial weight, the frozen weight of the main model. And B, A are the LoRA weights. Now you say, wait a minute, what does it mean in terms of, let's go back to our 4090 example or our A100 example. Suppose you're training a 7B parameter model, right? So to the foundational model for the forward, because in the foundational model, only forward pass happens, right? Only forward pass happens during fine tuning. You never back propagate through this. So you don't keep track of the gradients. And so you will, the memory utilization of this will be in the order of, let's say, 14 billion, 14 GB. Multiply, use 16-bit quantization, you would say that it's 14 GB memory will be used. Now, if you have, let us say that you're looking at only one little LoRa adapter, a tiny LoRa adapter, which may be, let us say 1 gig, 1 GB adapter. It can be even smaller. If you take a 1 GB adapter, that will contribute 2 GB for parameters. Another 2 GB.
1/7 of the original size.
Yeah, I'm just taking an example. And 2 GB, let's say for quadratic term, all of it adds up to 8 GB. 14 plus 8 GB is 24. Oh boy, you're still reaching the limits of your 4090. And then you have 20% overhead. So let's say that you have a slightly bigger, maybe a smaller model, 0.5 GB, 0.5 GB, right? Sorry, 0.5 billion parameter. This. So then it is 111, right? 111. And you get 3. Actually, it was 6. I miscalculated. It was 6. But then
20%.
Yeah. And then so then you have 16 plus 6 plus 3 is equal to 19. And then you add 20%. It's still about 21 GB. So you may say that, oh, you know what? I can fine-tune a model like that, perhaps on my little workstation. So obviously the benefits follow. The other benefit that follows is you don't fear catastrophic forgetting. Why? Because the model never changed. The foundational model is still there. So that was LoRa. Now, when LoRa came out, it was one of the most.
So can I? So
yeah.
What's the
microphone? Turn your microphone.
Oh, okay.
Yeah. Yeah.
Can you hear me?
Yeah.
Then what's the downside of the LoRa model? So
exactly. I'm coming to it.
Okay.
Yes. So now the thing is, as they say, there is no such thing as a free lunch. Right? This seems to be almost too good to be true. And so the problem that happened with LoRa is, what is it that we gave up? People found that the bigger problem with LoRa is, how do you know the right rank? Right? You don't know the right rank. You play a game, you guess 3, 2, 3, 4, 5, 6, 10, 15, whatever it is. And also, the best rank varies from layer to layer. Because there's so many layers, and everywhere you're sticking a LoRa adapter, AB matrix, LoRa adapter matrix, right? So what is the rank at each of these places? The traditional LoRa, the vanilla LoRa, just takes a fixed rank, a priori fixed 3, 10, whatever it is, and go. When you do that, if the rank is not sufficient to capture the semantics of your fine-tuned data, the performance of the model is not the same, of the fine-tuned model is not the same as if you would have fine-tuned the whole model and avoided catastrophic forgetting. So the basic vanilla lost a few percentage in performance, the model quality. How much you lost was a matter of debate and situation. In some tasks, you lost very little. In some tasks, you lost a lot. Nevertheless, LoRa took off and became very popular. Those of you who do images, right, or create images, create pictures, right, know that the image gen, like if you go to various image generation websites, or if you work with diffusion models, there is a galore of LoRa adapters. One will put, for example, put a spectacle or I don't know, something or the other. It will change the look. One will change the look this way. Another will give you the, Van Gogh look to the whole scene and whatnot. They are LoRa adapters. Good thing with LoRa adapters is they're composable, right? LoRa adapters are composable. You can take LoRa L1, L plus L2. You can go on composing and mix and match dynamically at runtime. You can say that, hey, make sure that the person has do this to the person, if there's any person in the picture. At the same time, give the entire picture itself a Rembrandt look, right? After doing this change. So you could do compositions with LoRA. So LoRA certainly has wide practical applicability. Then, considering the fact that LoRA has wide practical applicability, people began to ask this question: how do we mitigate the limitations of LoRA? So what are the ways that we can do that? So when they started doing that, they zeroed in, amongst other things, to two principal weaknesses or areas of improvement of LoRA. One is, we don't know what rank to pick, right? So the areas to improve are what rank are. And the second weakness was that, see, when you take a matrix and you do random initialization, right? The initial LoRA was initial weight initialization. Weight initialization means it's okay, you train the LoRA, but initially, when you created the matrix, what is the weight that you gave to it? How did you initialize the weights? You can't set it to 0, of course, that would be a catastrophe. It will never learn, right? So you have to give it some random weights. So typically, and this brings us to the interesting topic, in the traditional LoRa, you used key initialization. Key initialization. What is key initialization? It basically says that what you do is that you take, actually, there's a specific formula. You center it at 0, your random weights. You sample the, sorry, each of the weights, you sample off a normal distribution, which is centered at 0, all right? Right. But what you do is there's a specific formula. You take, so you put a sigma square, right? The variance, how spread out your bell curve is from that and this has a particular value. It is equal to specifically 2 over number of input parameters. So suppose in this layer, there are 100 and is equal to 100 at this layer. So the weight matrix here, when you initialize at this layer, you just do n is equal to 100. So it will become 2 over 100, right? So you use that. And as you realize, that's a very narrow 0.02, very narrow variance. And you have to initialize your weight from this. This initialization was very useful throughout neural networks because it actually ensured, especially when you use ReLU, the history is when you use ReLU activation, but generally more broadly also, that it would make sure that your signal, the signal transduction that takes place in the forward direction, you did not have either shrinking or vanishing values or exploding values. The signal neither shrank nor exploded. It was well behaved. It stayed within reasonable bounds. And so there's more. It isn't the only thing. Of course, you do normalization and batch normalization and layer normalization and other techniques are also there that help. But key initialization is something that people just assumed or took for granted that they would do. Now, key initialization has another variant, which is that you take it from a uniform distribution from 6 over n on 6 over n square root of this. Sometimes that also is considered a form of key initialization. So pick between the two, from a normal distribution or from a uniform distribution. So that is what it did. So the two areas that people found to improve on is these two: weight initialization strategies, so adaptive weight in some form, do dynamically or have a better sense of weights. And the other is adaptive rank. Don't make the rank the same across all the layers. Right? Why is that so? So let's take the adaptive rank first. See, suppose you have a transformer which has many, many layers. Layers. And each of them, you're putting a LoRa. Why should all the LoRa's have the same rank? It shouldn't have. Why? Because some layers, what happens is that are much more important, or they are doing more. So in the fine-tuning process, even the LoRa matrices should be bigger. Are you getting the intuition? They should be bigger. And some other layers are not contributing so much. So their LoRa matrices can be actually lower rank. They can have less parameters. So the rank itself should be a dynamic thing. And so that is one strategy. And the other thing is, the other is weight. How do you do weight initialization, right? So there is so both of these I'll very quickly mention. What people used to do is that they would do this. So let me do weight initialization strategy. Weight, like, let's just say that foundational model weight. Initialization strategy, or weight. Actually, the word that people use is weight-driven initialization. What it means is, this paper uses the word weight-driven initialization. What it means is this. You have the foundational model. In the foundational model, at this level, you have the weight matrix, and then for which you're trying to make a corresponding LoRa, AB matrix, right? So this, you're trying to find a corresponding value here. Now, what you can do is this. So weight initialization means you take whatever rank you want to take. So let's say that you chose rank 5. AB is fixed. But now still the question is, how do you initialize the weights of LoRa? How do you, the question you answer is, how do you init the LoRa weights? Weights. Yeah. And the answer that people give in this is, like, see, look, guys, this foundational model, the weights are there for a reason. It has picked specifically those weights because it has learned something, right? And so why don't we ensure that the knowledge of the foundational model sort of informs our choice of the LoRa weights? Are we together? If we can take the knowledge of the foundational model to benefit this, then we would have a winning situation. So what people do is they do something called a singular SVD, singular value decomposition. Which, very briefly, given a matrix M, or here the weight matrix, it can be written as U, a diagonal matrix, and a V transpose. Because it can be written that what you do is you use sort of U and V to create your A and B matrices, right? So people have used this strategy. And the reason it works is because you benefit from the learning of the, it sort of captures the important structural information that the weights, the foundational model has. And because of that, the benefit that happens is your training, your fine-tuning is faster. You're not initializing from a random state. You're initializing from some known knowledge, which you're refining in the adapter. So that is one of the big, and so it's a very stable learning. You don't see the weight, the weight swing too much in the LoRa. Right? They very quickly converge. They have a very systematic, stable path to convergence. So, and then of course, what they observed also is that this weight-driven initialization with singular value decomposition also leads to a better performing LoRa. That it has higher performance. So that was one idea. The second idea is adaptive rank allocation, of which DORA, I suppose, is a good example. What it says is that let the rank of each of the layers be different. So then the question comes, how do you determine the rank of each of the layers? So what it says is, look at how important the layer is to the fine-tuning process, how much it captures that. And so how can you do that? That is easy. If you notice, so one of the easy ways that you can do that is look as the LoRa is being fine-tuned, look at the gradient of the loss with respect to the weights there. High gradient means what? High gradient means a weight is being very sensitive to the new information, isn't it? Because what is derivative is sensitivity. In very intuitive terms, if the slope, derivative is the slope, right? So imagine that you're going uphill. If you take 2 steps forward and you have already risen 3 feet, you would imagine that the slope is high, right? Your height is very sensitive to the location. You move barely a couple of steps and you have climbed a lot. So it's high sensitivity, which changes a lot. That's what derivative means. Derivative is nothing but sensitivity, right, to the input, of the sensitivity of the response to the input, right? And now, if you notice that in some layer, the weights are highly sensitive to the derivatives are high, the gradients are high value in absolute term, what does it tell you? That layer has a lot to learn from the fine-tuning data, isn't it? So it makes sense that for sensitive layers, increase rank, isn't it? So you do it by studying, by passing the data through the training process, by passing the data in the backpropagation phase, by observing what the gradients come out to be. And if the gradients are large, then you increase the size of that. So rank, therefore, becomes rank is adaptive. So rank adaptive, right? And so the formal name of this approach is, well, is writing it backwards. They call it adaptive. Rank is adaptive. Adaptive. Did I write it correct? EDAPTIV. Adaptive rank allocation. And this paper talks about both of these strategies of weight-driven initialization and adaptive rank allocation. Now, you would imagine that it is a good idea, certainly, to use both of them. So there has been a whole set of approaches. Some used one, some used the other. What this paper did is it did 2 things, essentially. It said that, let's do one thing. Adaptive rank allocation is a wonderful idea. You should test out how much rank you need at each of the layers. So let's consider that to be a given. The second thing it says is that a weight initialization also needs a methodology. So you could have said, well, let's just put these 2 ideas together, but they went one step further. What they said is, see here, we learned the weight, the LoRA. So pay attention to this figure. The weight matrix of the foundational model informed the LoRA weight initialization, isn't it? But what this paper says is something quite different. It says that do it differently, actually. Don't use the weights. Use the data. So that's why they call their approach data-driven initialization. They propose data-driven initialization. But initialization of what? Of AB weights. Right? The A and B matrix weights. Data-driven initialization. Now, what in the world can that mean? What you do is, let's say that you have a layer that has, let's say, 100, whatever, 100 neurons. You give it a mini batch of data, right? Let's say that you give it the first data point, mini batch of data, give it a data, let's say, why did it suddenly become so? Sorry, I don't know why it became so. Okay, I'll just use, apologies, something weird happened. So suppose you give it. Now, each of these data points will go through this. What will happen through each of the neurons? Each of the neurons will produce its activation, isn't it? If you take just one data point, let's just take this data point, it goes through all of them. It will go through, it will become the activation function of w dot x plus b, right? The weight matrix, right? You will get this, right? Now what you do, w dot x plus b activated. So you will end up with activations. You will have activations A1, A2. So what will happen is you will end up with a matrix. Each of the sample points. So suppose you take 10 sample points. You will, or let's just take, or 5 sample points. 3, 4, 5 sample points. And each of these will be a 100 column vector because each of the neurons will fire. They will fire, and then you will have A11, A12, A100, because the 100th neuron for the first data point will fire. And then here, let us say that you gave 5 data points, the 5th A51, etc. So you'll end up with an activation matrix, a matrix of activations. What this approach is saying is something very interesting. It is saying that look at these activations for fine-tuned data. What should happen, or what will happen, is that this activation is telling you which of the weights, or what is happening in the weights, right? What are they doing? Don't matrix factorize the weights themselves, but matrix factorize these activations, right? And the way you do the singular value decomposition, what you do something magic called. So let me just take, so this, in this paper, they very interestingly call it X of the layer I. This can be written as U V transpose, of course, the same singular value decomposition as a product of 3 matrices. The inner matrix is always a diagonal matrix. And what it says is that, see, look, this matrix that comes out, it is made up of certain vectors. So if you look at this V matrix, and this is a little bit of linear algebra, but just think of it as a V as made up of certain vectors, V1, V2, right? V whatever, Vk, these vectors. What your machine is saying is that, in a sense, the data can be represented best by this. And I'll give you an intuition of singular value decomposition shortly, but for now, just believe me. Now what you do is you ask this question, which of these vectors really matter, right? And then you sort the vectors by how much, and I'm giving an intuitive explanation, and then I'll get a little bit mathsy, so that those people who want to avoid math can just, after that, pause. Sort the vectors by how much they matter. How much do they matter, right? And then, so you'll come up with a different sorted order, V2, a different matrix will come up here, etc. And then what you do is, just say that only give me those vectors that totally, in some sense, might help explain or are responsible for, let's say, 90% of the information, right? And when you do that, you might realize that only 10 of these vectors are needed, right? And when you pick only 10 of them, what you're basically saying is that I am looking at a space which is only 10 dimensional, because a 10 vectors can span a 10-dimensional space. That spanning space is the rank of your AB matrix, essentially. Right? It is explicitly the rank. And so the main idea, so now I'll go back to this paper. I will put on hold explaining what in the world this SVT is. SVT is a crown jewel of linear algebra. It's just amazing. And machine learning, I can't even imagine without SVT. Uh, so let's read this paper. What they say is that you can learn these. And by the way, you said that, oh my goodness, so when I'm doing fine tuning, do I have to send mini batch after mini batch after mini batch of data to find these vectors? They say don't do that. What you should do is send a mini batch, you find some vectors, you find the best vectors, and then send another mini batch, and then you notice that the vectors that they predict are slightly different, right? So now you small changes, and you do a few more mini batch till you notice that those vectors, those small vectors, are not moving much. You say, okay, I'm done. So it's not that you use it throughout the fine tuning. You just do it with a few batches, mini batches, and soon you know your answer. And then you say, I'm done. Are we together? And you use those weights as an initialization for A. And then you do the rest of the training. You treat it like a normal LoRA, because all you're doing is you're using it to find two things. First is what is the best rank, right? And the second thing you do is find how to initialize the matrix, the A matrix, right? And so you basically in one shot are able to do both of these. That is the main idea of this paper. So now let's read this paper. This is what it says: data-driven initialization. Our aim is to find an efficient, and I'll just read highlight the sentences I'm reading, is to find an effective initialization for the low-rank matrix A in a data-driven manner to maximize performance on the downstream task. To this end, we perform SVD on batches of activation vectors. So why batches? You send mini batch, you'll get batches, many batches of vectors. So there's to obtain the right singular values. So what happens is that in a singular value decomposition, the right matrix is the matrix of right singular values, right, or singular vectors. So, okay, so now let me go back to the paper. And once you get this idea, guys, the main idea of the paper is just in just 2 pages. You take this, and so I wrote it as, if you remember, I wrote it in a more traditional notation, U sigma V transpose. Here they have broken it up down into components, right, that matrix. So U sigma, and little v, that's the main idea. And basically they are saying that initialize the A of the LoRa adapter, to the right singular vectors. Now, that all seems very magical. And how do you determine this whole concept of importance? So which vectors are important and how they are important? It turns out there is a bit of mathematics. It's that you do learn. It is called the explained variance, or the proportion of variance explained, right? There are various words. And there's some related formula. This is one of the easier ones that says how much it is explained. And that's very simple. You just say that this particular eigenvector, or not eigenvector, singular value vector, has this much variance of the data that it explains. Now,
gradient.
No, variance. Variance is a different term, and I'll come to what variance is. But just take me. The variance is very specific to SVD itself. Now, what does that mean? This is where typically it gets a little bit heavy, because you realize that the main argument is given in just basically this little bit, section 3.2 and 3.3, right? And the rest is the results after that, experimental results. But results are very impressive. You can clearly see that it is doing very well. In particular, pay attention to the last line here. Right. So when you take this thing, it is doing very well. Now, I'll just mention 2 things. When you do singular value decomposition, obviously I'm parking the explanation of it. So for now, take it for granted. 2 things matter. The direction of the vectors, those vectors that we found, singular vectors, and how big those vectors are, magnitude. So direction and magnitude. So one of the questions that comes in this paper, and they do ablation studies. Ablation studies means how important is each factor. So they ask this question: what if we throw away, like we jumble up the sizes? They realize that if we jumble up the sizes, the algorithm degrades. What if you replace the directions? You jumble up the directions. You don't honor the directions of those vectors, but you keep the sizes there. It turns out that it gets even worse. Directions matter, really matter, right? So it again speaks to the fact that singular value actually does contain a lot of valuable information, but it's not the singular value of the weight of the foundation model, it's the singular value of the activations derived from the singular value decomposition of the activations. That is the main thing. And the results everywhere are consistently very good. If you look everywhere, this approach, joint approach does much better, right? Well, I wouldn't say much better. I would say, well, let's just say it does better, right? In LoRa adapters, you're fighting for decimal points, right? So it does a little bit better. Now, I will end the talk by just giving you an intuitive explanation of what I said about singular value decomposition. But instead of explaining the gory mathematics, I will do something adjacent to it. I'll give you a very simple physical intuition into what it all means. But I will first start by explaining a cousin of singular value decomposition. It is called eigenvalue decomposition. So we will take a cousin, close cousin of SVD called EVD, eigenvalue decomposition, eigenvalue decomposition. The two are very related, by the way, but I'm deliberately doing it. And because I want to give you the intuition of what it is. So see, guys, suppose I'll give you two situations. Suppose I give you points like this. Data points that are there. Now you realize that this is basically data that is in a circle, right? Uniformly distributed or normally distributed in a circle, right? So for example, this could be X belong to a two-dimension, and it may be sampled of a two-dimensional bell curve, Gaussian, right? Two-dimensional normal distribution. Are we together? Or you could take it uniform distribution, whatever, it doesn't matter, right? This data. What is the, so suppose this is X and this is X1, X2. What is the covariance between X1 and X2? What is the correlation of covariance between? A co-varying means if X1 increases, do we notice that the value X2 also increases for the point? That is not true. Half the points are on the opposite side, isn't it? So there is the covariance is equal to 0. Or simplified way, if the data is normalized, then it is correlation. So what is the correlation between X1 and X2? Is 0, isn't it, guys? One doesn't seem to have, X2 doesn't seem to be in any way related to X1. Right? On the other hand, suppose I give you data like this. The same data, the same number of points, like this. Now, are X1 and X2 correlated? Certainly. If you increase X1, X2 also increases, isn't it? So you would say that the covariance of X1, X2 is certainly not equal to 0. In particular, it is greater than 0, right? It has a positive covariance. So from this, now observe, the former has no relationship. The latter has relationship. It's a linear relationship. So let's look into the world of linear relationships. You can therefore say that a linear relationship between two variables, right? So if it helps you think in terms of, let me just make it X and Y. Y as a response variable, X and, let me write it as X and Y. X, Y is greater than 0. Now you say that if there is a relationship, linear relationship, then Covariance is greater than 0. Now, also notice an interesting fact. If you take any point x, y, and multiply it by a matrix M, what it will do is it will take that point, let's say that the point is here. This was xy, right? It will, point P, what it will do is it will produce some other point x prime, y prime, isn't it? And this point may be somewhere here. Let us say that it went from here to here. This is P prime, that is x prime, y prime. So this point has the matrix M has transported this point from P to P prime, isn't it? Now, if you think in terms of P and P prime, you may, and this is a little bit of a fact, I'll tell you, it is partly rotation and partly stretching or unstretching, like shrinking, scaling. It's partly rotation and partly scaling, isn't it? You can convince yourself that you can first rotate and scale or scale and rotate. You have your pick, shrink and rotate. You can do that. So therefore, the fact that points get, all that matrices do is move points around. That's one way to think of it. So then you can ask yourself, is there a matrix? Is there a matrix M such that it takes this and converts it into that, right? Converts an isotropic distribution like this and converts it into a relationship. You would imagine there has to be a matrix. So there is some matrix. And what would that matrix really contain? Well, you realize that if this has structure, which is given by covariance, the matrix M somehow has to be related to the covariance. And in fact, it is. That matrix is equal to covariance XX, that is nothing but sigma squared, covariance XY, covariance XY, covariance YY. And of course, this is sigma X squared, this is sigma Y squared. This is your matrix. It just so happens. I won't get into the detail, but that is the basic intuition, right, of that. Now, the beautiful thing is, so every matrix will take an isotropically distributed set of points, which has no relationship. And if you convert it into a linear relationship, if it makes a linear relationship, then observe what can you do. You can shrink wrap the data into an ellipse. Would you agree that you can shrink wrap the data into an ellipse? What is the nature of an ellipse? An ellipse has two axes. The principal axis, the major axis, and the minor axis, isn't it? Does it make sense? And I can give it two vectors, E1 vector, a unit vector in this direction, and I can have a unit vector E2 in this direction, isn't it? Now observe something very interesting. In the direction of the unit vector, a point that was here, it only got moved from here to here, isn't it? It only got stretched. All the points that would fall on the two axes, those major and minor axes, they only get stretched. All other points go through some rotation also, isn't it? Right? Now you can ask this question, on the first axis, how much did the points get stretched, scaled? They would get scaled by some amount, lambda1. And on this axis, they got either scaled or shrunk by lambda2, right? On the other axis. Now here is something beautiful. This matrix M can be written as, you just take this matrix, unit vector E1, E2, right? This is called the U matrix, because this unit vector will have two components. It's a two-dimensional vector. Times a diagonal matrix D, which will have this structure, times the transpose of this. right? So it is U, D, U transpose. And you can convince yourself that for unit matrices, people also write it as UD, U inverse, right? So what is the intuition, therefore, of eigenvalue decomposition? Any matrix M, when you decompose it into eigenvalue, square matrix, when you decompose it into eigenmatrix, in a sense, you're doing the same thing as you do with numbers. Suppose I give you a number 42, and you say, it is made up of the primes 2, 3, and 7, right? In some sense, you have unpacked 42 and understood 42, the structure of 42, isn't it? In the same way, we say that any matrix, to the extent that it can take, and if you just think in terms of these dot points, I can unpack it into 3 vectors. Well, actually 2 vectors if it's a square matrix, U and D. U is made up of the direction vectors, and D is made up of the scaling factors, isn't it? Scaling vectors, right? Scaling, magnitude of scaling, which is dead obvious when you look at it geometrically. That is what is happening, isn't it? So this intuition that is true for square matrices, right? This M is a square matrix because you're transforming from 2-dimension to 2-dimension. If you now generalize it to going from n dimension to m dimension, the same arguments apply, right? The relationships, a linear relationship, if you can think of that matrix, it will be. And in the case, the generalization of singular eigenvalue decomposition to non-square matrices is singular value decomposition. And so this, given the fact, so just for a moment, pretend that we are not talking SVD, but eigenvalue. Why do those directions matter? You see, in eigenvalues, the directions matter because they really capture the essence of the data of the matrix. So suppose you have a weight matrix, and just for a moment, just imagine that it is a square weight matrix, and you're doing eigenvalue. Then obviously, you imagine that any square matrix, weight matrix, its eigenvectors matter. Those directions matter, and scaling factors also matter. And so in a more general case, SVD, the similar things apply. Singular vectors, singular value vectors matter, and they will, now notice that. Is the variance more in the first direction than the second direction? E1 versus E2? The data is much more spread out around this, right? So you can say almost that 80% of the variance is along this axis, and a little bit of a variance is along, let's say, the other axis, minor axis, right? So what you can do is, the way people think about it, why does that matter? Suppose the data is like got distributed like this. Got distributed even more skewed, and I'll just make a picture. All of it is very tight, and you did envelope, and your envelope is very pencil thin, like this, right? You realize that basically you have reshaped your spherical data, circular data, into what is essentially a line, right? You can just ignore the second vector altogether, isn't it? And in fact, that is, in linear, you do that. It is called principal component analysis, if you remember from your basic machine learning. Principal component, what we are looking at is principal component analysis. And in a sense, what you're saying is, if certain vectors have much more variances in their direction, then overall data variance is mostly explained by them, then the other vectors, we can just forget about it, isn't it? And that is the argument they are using. The reason you use SVD, whether you do weight-driven initialization, or in this particular case, data-driven initialization, the reason you do the SVD of the matrices is because by doing SVD, you come up with the singular vectors, and you need to keep only a few of them. You can throw away the rest. But when you keep a few of them, what you're saying is data can be described by a much lower dimensional space. In other words, it has a low rank. A low rank is exactly what you're searching for. And in fact, the values of the right singular vectors is the initialization of your A matrix, and the rank automatically came out from that by just picking those vectors that principally have most of the variance. Right? So that is the mathematics behind this paper. So that is that, guys. Any questions pertinent to this or that I can answer to help clarify this?
A question tangential.
Yeah, please go ahead.
Okay, when you wrote out that ellipse, that warped ellipse in that second space, why are the two principal axes perpendicular to each other? Is there something that forces that to happen?
Yes, it forces that to happen. Orthogonal. You're basically saying that, and
But
there is
why not? Why are the two principal axes necessarily perpendicular to each other?
see what happens is that whenever it is called the spanning spaces, that x and y are perpendicular to each other, you are searching for another spanning space. Whenever you look for a spanning space or a subspace, the underlying assumption, almost axiomatically you assume, is that in the spanning space, you see, suppose look at 3 dimension, you have 3 perpendicular axes. But if let's go back to our, I mean, I wouldn't completely answer because it gets a bit messy, but here's simple. Suppose data is on a plane, right? Now, X, Y, Z axis are perpendicular, but the moment I realize that data is on a plane, you could take 2 vectors which are non-perpendicular, but then there is entanglement between the vectors. The most efficient way to describe the points on a plane is to once again choose 2 perpendicular vectors. So the 2 perpendicular vectors are deliberately chosen because orthogonality gives you an sort of untangled description of the data. That is one. The second thing is, that is the general statement. In the case of this, a matrix applied to data point like this, it just, when you work out the math, it turns out that it will convert it into an ellipse. And the ellipse, you have one vector and the perpendicular vector to that, right, will be, and a third vector, suppose it was 3-dimensional, something perpendicular to both of them. Those would be the vector. The first vector would have the greatest variance. The second perpendicular vector would explain some of the variance. See, think about it this way. Here's a basic example. Suppose I didn't take that. Let me choose another color. Suppose I took E2 prime here, which is non-perpendicular, right? Or let me deliberately make it visible. It's not visible. Let's say that it was in this direction, some other direction. Now what happens? The variance of the data in that, like how important that axis is contaminated by the fact that when data moves forward along E1, it also seems to move forward along E2 prime, isn't it? So how would you know how much E2 prime explains the variance in the data? You won't be able to do that. The only way you can do that is if you take an axis along which data doesn't is sort of orthogonal to E1, right? To really know how much data, the variance of the data in that direction matters. That's why you always pick orthogonal directions. I don't know if I answered that well for you.
Sort of. I mean, I got to think more about it.
Yes, it is. It isn't easy. Let me just say that I gave you a hand-waving argument and try to make it intuitive. But unfortunately, this is, you hit a point at which, unfortunately, now we need to sit down with the linear algebra textbook and read through that section or through that part to get it, to work it out to get a sense of that. All right, guys. Any other questions? Let me stop the recording.